Hello, dear students. I'm just trying to share some thoughts with you on Project 3. So, the third module of the course. This is not like a formal revision, but rather than sharing the main concepts and the main ideas. So, main technical concepts. So, what are the main technical concepts? The first thing that was discussed in Project 3 or that you have addressed in your Project 3 is digital modulation. Right? And the important things that have been addressed related to digital modulation are types. Okay, so we have ASK, PSK, QAM, and we have a special type which is FSK. These three types are called linear modulation, linear digital modulation techniques, and all of them have classical constellation diagram. Okay, so what does the constellation diagram show? The constellation diagram is a real and imaginary, so it's a complex domain diagram that shows the possible points, the possible symbol values as complex numbers for a particular. For example, this is just an example. This is a 4 QAM. Okay. So in 4 QAM, there are 4 possible values. It's I plus j, I minus j. Sorry. It's 1 plus j, 1 minus j, minus 1 minus j, and minus 1 plus j, where j here is the root of minus 1, right? Now this is for a unit, right? Energy case, okay? The constellation diagram, number 1, so A, it shows the possible symbols coming out of a modulator. Number B, the radius is proportional to energy for a symbol. Sorry. Okay. So here, this one has unit. So this has a radius here equal to 1, right? If it has a radius equal to 1, so these are gonna be, rather than 1 plus j and 1 minus j, they have to be the half, or 1 over root 2 and 1 over root 2, right? So that when you add them, they give you a unit energy. So all of this for the unit case is gonna be, all these are gonna be multiplied by 1 over root 2. Same here, 1 over root 2. Same here, 1 over root 2. Same here, 1 over root 2. So when you calculate the length, that length becomes equal to 1, right? So this is going to be 1 over root 2, and this is going to be 1 over root 2. This is for a unit energy. Now, if the energy put into the transmission is more than a unit, then this constellation diagram will have a bigger radius. And if it's less than a unit, it's going to have a smaller radius. So basically, you can use the constellation diagram, use constellation to calculate energy for each symbol and the average energy per symbol, right? And if we have Emery modulation, then average energy per bit is equal to average energy per symbol divided by log to the base 2m. What is this? This is number of bits per symbol. So I can also calculate the energy per bit if I want to do that. And the way to do that, the average energy per bit, is basically to calculate the average energy per symbol and then divide that by the number of bits in any symbol, which is basically log to the modulation index, right? How do you calculate the average energy per symbol? You have to calculate the energy for each symbol, add all of these together from the constellation. The energy is simply going to be the square of the length for that symbol. So for example, here the energy for this symbol is 1. All of these will have an energy equal to 1, which is square this length, right? If I had some point here, for example, I would draw the length to that point and then get the square of that length from the geometry of the constellation diagram, right? And then I calculate this for all the symbols, add them together, divide by the number of symbols. This is going to give you the average energy per symbol. And from that, you can calculate the average energy per bit if you want, right? Another important thing which is addressed as well in the constellation diagram is, and I will try to fit this here. So the other thing which is important also in the constellation diagram is the definition of detection, symbol detection regions. Symbol detection regions, right? Again, the whole idea, depending on your modulation, let's say, for example, your modulation was 4 QAM. We know that the possible symbols are those, the 4 symbols of the 4 QAM, right? But the problem is, after transmission through the channel, I might receive something like this. So I don't receive an exact symbol value because of the noise in the channel. So when I receive something like this red dot that we see here, for example, minus 0.1 plus 0.6 J, what should I say that was the transmitted symbol? In order to do that, we go between the symbols, we divide the region between them such that the dividing lines are the lines that have exactly the distance between each 2 symbols. So eventually I end up with 4 regions, right? This is 1, this is 2, this is 3, and this is 4, right? So I end up with 4 regions, and whatever symbol I receive, depending on the region that it falls in. So for example, this one I received like this. then I will, since it is in this region and this region is around this symbol, then this is gonna be mapped to this. So if I receive something like this, I will say that what I received is actually -1 minus j. Okay, so I received this symbol and so on. So I can overcome the noise and do detection of symbols. And then after detecting the symbols, I will use the mapping between symbols and bits to actually decode the received bits. Okay, so that's basically an important. For example, in the case of PSK, let's say 8 PSK, for example, then it will look like this, right? The symbols that we have, sorry. So 8 PSK will look like on a circle, right? And it's quite easy to see that the lines that does the division correctly is this, right? So the ones that passes through the middle points between each 2 points, right? And these becomes your regions. So this is one region, this is the other one, this is the third one, this is the fourth one, and so on, right? And again, when you receive something like this point, you will simply map it to this, since it falls within the region of this one. So one of the things that you need to be able to do is that given a particular constellation diagram, you should be able to define the regions of detection, and then given a certain received symbol, you should be able to tell me received after noise. You should be able to tell me what was actually transmitted or what will be assumed as the transmitted one. By looking at, after you do the regions, you look at those regions and figure out where the received value falls, and then accordingly figure out the corresponding symbol as described here, right? All of these things are done through the constellation diagram. So given a constellation diagram, you can do energy calculation. Given a constellation diagram, you can do the energy here means the average energy per symbol or the average energy per bit. Also given a constellation diagram, you should be able to figure out which modulation is this, right? So that's something that you have to keep in mind. And that's for the 3 linear modulation methods. And given a constellation diagram, you should be able to define the regions and do a detection if required, right? A detection of a particular transmitted noisy symbol that you receive somewhere, okay? Another important thing also corresponds to the constellation diagrams is the mapping. So we have the mapping, bit to symbol mapping, right? You can also show that on a constellation diagram. Let's say, for example, I can give you a constellation diagram and I tell you that these are coin points and they are labeled or mapped. This is called also labeling. Okay, as let's say 0, 0, 0, 1, 1, 0, 1, 1. There are many ways for doing the mapping. We did not really study for the labeling. We did not really study those, so that this will be basically given to you in one description or the other. You should be able to put it on a constellation diagram or figure out based on the given labeling scheme which symbol is going to be transmitted from the constellation diagram possible symbols. Okay, that's also another important feature. Constellation diagrams can be also used to calculate bit error rates, but we did not go through that in this course. You can study that in courses that talks more about digital communication systems in advanced courses. Okay, the second in this course was the pulse shaping idea. Pulse shaping and optimal detection. These are two tied models or concepts. Okay, Now, pulse shaping, what's the idea of pulse shaping? I think all of you knows that the whole concept of pulse shaping is that I change. So in pulse shaping, the objective to use some time shape for bits or symbols other than rectangle. Okay, so if you want to send some data, the typical way is that you are gonna say data in terms of symbols or bits. Let's take the simpler example of bits. You will send one bit for a certain bit duration TB, which is gonna be a constant value, and then another bit, maybe 0, for a certain, again, bit duration TB, and then a third bit, maybe also 0, for duration TB, and then a fourth bit, right, constant, and so on. So in these cases, the shape of each pulse, the shape of each symbol, is a rectangle with a certain height, right? It can be, by the way, 1 and the zeros are -1, right? Okay, so it doesn't always have to be ones and zeros. Most commonly in communication systems, it's +1s and -1s, okay? So the whole idea is that any pulse, any symbol, any bit, even if you are sending symbols, they will have different magnitudes, but they will be transmitted as constant values during the duration of the symbol. So we call that rectangular pulse shape. The problem with that is that, as all of you almost have described, is that this, because of the abrupt changes that happens at these points, right, it causes actually, the abrupt changes happens at these transition points, right, when you transition from one value to the other. It causes, in the frequency domain, it causes a large amount of components in a large band of frequency. And accordingly, since the channel already has some bandwidth, it does not allow all the frequencies to pass through, then this will mean that in time domain, it's almost impossible to have this quick transition, and things will be smoother, and then accordingly, intersymbol interference will happen, as described in the literature, as described in the resources that you have seen, and as many of you were able to describe that. So what do we do to overcome this? We need to use something different from the rectangle. This is where we come to the Nyquist criteria, and particularly we considered only the first criteria. So Nyquist criteria 1 says that if you want to use a good pulse shaper, it must have two things. Number one, it's band limited. And number two, at locations of sampling other bits, it has to be 0, right? Now, what does this mean? It means that when I look at it from the frequency domain, the pulse shape that I use, when I look at it in frequency domain, it should not go to infinity. Remember that the rectangle in frequency domain will have a sinc function, right? This is rectangle in time, and in frequency, it will look like a sinc function, and accordingly, it will have an unlimited band. It goes all the way to infinity without going to 0, right? Now, we want it to be limited in frequency. And the second thing that we want is that in time domain, so this is in frequency domain, and then at locations of sampling, so this is time domain restriction. This is frequency condition, and this is time domain condition, that at the locations of sampling the other bits, the pulse shape of the current bit should not interfere, should have a 0 value. One of the possibilities, it's not the only one, is something called the sinc pulse shaper. Sinc pulse shaper will have something that looks like this. In time domain, each value is transmitted using a sync function, right? The nice thing about the sync function is at the peak here, it will have a value equal to 1 multiplied by whatever the amplitude of your bit, 5, 3, whatever voltages or amplitudes that you are using. So each bit is going to be transmitted using a sync function. The first bit is transmitted here. Second bit will come at a shift. Remember, one bit from the other, they are shifted with a value TB. So the second bit will come at this location, right? Okay, and it will be peak here, and it will go to 0 here, and then continue. Same thing here, and so on. Third bit is gonna come at shifted by TB again, right? Okay, and the same story continues, right? Notice the nice thing that's happening here. What's the nice thing? At the peak of this bit, all the others, they cross at 0. At the peak of the next one, which is the sampling point at the receiver, I will sample at this location, at location TB, to get the second bit. All the other bits, the sync functions of the other bits, will have a value 0. At the peak of the third bit, at time 3 TB, all the others will have a 0, and so on. So basically, at the points where I read the bit value from that pulse shape, I will read a single value, sampling. So that value will be at the peak, and at the peak of each one of them, all the others are 0. So accordingly, theoretically, I don't have intersymbol interference. So basically, and if we look at the sync function in time, we know that it is in frequency a square. This is in frequency. This is time, right? So we know that it looks like a square in frequency domain, which means that it is band limited. So this achieves the band limited condition, and this setup achieves that they don't interfere at the sampling locations of each bit, right? So that's one possibility. There are other possible pulse shapes that achieves the two parts of the first Nyquist criteria, but we only looked at the sync pulse shaper, right? So remember that what's transmitted in time domain actually are those shifted syncs. Each one of them represents a bit. Again, practically you cannot send the sync function because it's expand all the way to infinity, but you will send a reasonable duration, which means that in frequency domain it will not look like this exactly, but it will be slightly different, but that's fine within practicality condition. Now, what happens at the receiver side, okay, in order to do this detection or sampling of the bits, we use what's called the matched filter as an optimal detection. So optimal detection. Tamam. Both the designs of optimal detection has two designs. They correspond to each other. I'm not going to describe them again here. Should be able to describe them in block diagrams. So you should be able to show them in block diagrams and as equations. Okay, those two designs are the matched filter and the correlator receiver. Okay, both of them are more or less, they perform the same. They have some advantages and disadvantages over each other. Should be able to show their block diagram correctly. Understanding where they do the sampling. So each one of them, after a certain number of blocks, it has a sampling at point TB. Should be able to describe the conditions for optimality. So conditions for these filters, to be optimal. We call these conditions for optimality, particularly that we are using polar, so we use +1 and -1 for the transmission of the signal. That we are using we are working under additive white Gaussian noise. So under using polar and with additive white Gaussian noise as the effect of the channel, the matched filter or the correlator receiver is optimal in terms of minimizing the probability of making a mistake. So you should be able to mention those important conditions as you did already, or many of you did in the project. And then after that, you should be able to show the block diagram of each one of them and perform the operation. So the operation is written. So if I ask you what is going to be the output from this matched filter given a particular input, you should be able to calculate the output as you did in one of your assignments. So that's the optimal detection part. Given one of them, you should be able to draw the equivalent, the other one, if required to do so. And also you have to mention why we sample at TB, why we do not sample at greater or smaller value than TB, and that's also mentioned in some of your resources. So that's the second part that we talked about, which is pulse shaping and optimal detection that we looked at. The third part that the course goes through is the bit error rate calculation for binary PSK. So we are using the 2 PSK, right? Under additive white Gaussian noise. Right? For this part, we started by discuss random processes and their types. You should know those types and what are the differences between one type and the other. So the stationary, the white sense stationary, the ergodic, and then the general random process, right? And then the second thing is represent noise as a random process, right? Where it is additive, it's white, so it spans all frequency. It's Gaussian, so its statistical property it follows a Gaussian distribution. So additive white Gaussian noise should know the properties that its autocorrelation function Rx of noise, right, is equal to a delta multiplied by n naught delta of tau, and the corresponding power spectral density for that is a constant value equal to n naught, and also that for noise the power spectral density is equal to the variance of the Gaussian distribution of the noise, right? So you should be able to figure out these things from each other, know this important property. Also given a particular random process described to you. So here, in addition to knowing the types, you should be able to calculate the autocorrelation and the expected value, right, of x, right, and Rx of tau, right, and from that figure out whether this is a white sense stationary or not, and also should be able to calculate the power spectral density, which is basically the Fourier transform only in the case of white sense stationary. So it is the Fourier transform only in the case that your random process is white sense stationary. Otherwise, if it is not white sense stationary and you are asked to calculate the power spectral density, you can simply say it cannot be calculated and that's it, right? As I mentioned also, you need to be able to represent noise, and then number 3, follow the procedure. Should be able to follow and understand the procedure of calculating the bit error rate for BPSK. In particular, you need to understand that the effect here is noise. Noise follows a Gaussian distribution, right? Because when we transmit, we either transmit +1 or -1, or we call that plus AP and minus AP. So actually, when we are sending +1, we end up adding a constant to a noise, which is Gaussian, and the noise has a zero mean, so the transmitted in that case is gonna be something centered around the magnitude of the +1, and in the case of sending zero is gonna be the other way around, centered at minus the magnitude of that. And then the definition of error is that one is transmitted, and then I think at the receiver that it is zero, which covers this region, and the other way the other region. Because of the symmetry, I can calculate one of them and multiply it by 2, right? And then that's the probability of error given 1 is transmitted, and the probability of error given 0 is transmitted. I have to multiply that by the probability of 1 and 0. Also, if the detection threshold is not here, maybe let's say that the detection threshold for some reason is something other than 0, to say that this is a 1 or this is a 0, then the area that you need to calculate is going to be the bigger area for this curve and the smaller area for the other curve coming after. So, for example, if these are the two curves, right, around the AP and the minus AP, and you were told that the threshold is not 0, it's somewhere, maybe it's 0.5, for example, then the area of the error is going to be this area under the curve of the when 1 is transmitted, and then added to it, right, this area under the curve when 0 is transmitted, right? So it's no longer symmetric in that case, and you have to calculate each one of them. So you should be able to perform this operation and calculate the bit error rate if I change some of the parameters of the system. What are the different parameters of the system? The probability of 1 and the probability of 0, which are complement to each other. So these are one parameters that might change, and you will ask to calculate the bit error rate, or the energy, so AP value, and that's gonna change or the sigma square of the noise, that's another parameter, or another parameter is the threshold to decide 1 or 0, right? In the derivation that you did in the literature, or you find in the literature, the threshold is assumed to be 0 value. So if it is greater than 0, I say 1. If it is less than 0, I say it's 0, right? So if it's less than 0, I would detect 0, and if it is greater than 0, I would detect a logical 1, right? Or AP and minus AP, right? However, it might be not compared to 0. It might, for example, be greater than or less than maybe 0.1 or 0.2, depending on the design of the system. So the system might be deciding that what was transmitted is 1 if the value of the received signal is any value greater than 0.1 rather than 0, and what was transmitted is 0 if the value of the received signal is less than 0.1. So in that case, you need to still be able to calculate the bit error rate in that situation. And the last thing is to calculate signal to noise ratio, or to represent the bit error rate as a function of the signal to noise ratio. And the signal to noise ratio is signal power, okay, divided by noise power, okay, which is equal to AP square divided by bandwidth multiplied by n naught, and then this is also equal to the energy per bit of the signal divided by n naught. So you should be able to represent it this way or that way and understand the relation between them, and calculate the signal to noise ratio for a particular given setup. Okay, so that's more or less the things that we have looked at. The last thing is to be able to find bit error rate for given SNR or EB over N naught, whichever, both of them are SNRs, from a curve. So you'll be given the curve of the bit error rate versus SNR, right, versus EB over N naught for a particular modulation, and then you are asked for a given SNR, what's the corresponding bit error rate, or to get a certain bit error rate, what is the required SNR. You can get any one from the other. You just have the curve, and you should be able to use that curve to do that calculation. Now that's a summary of the concepts that you need to keep in mind. And inshallah, I wish you all the best in your exam. You don't need to worry. You have done a lot of effort to go through your projects and assignments and so on. So should be fine, doing very well in the exam. Thank you.